Good afternoon, everyone. My name is Riccardo Fricata. I work together with Professor Tosumi at the Joint and Welding Research Institute on Osaka University. Today's presentation is the first of two presentations. Basically, I will introduce the feature of a fully coupled elastoplastic and damage model and test it under monotonial tensile test. In the next presentation, which will be given tomorrow, I will show a modification of the damage criteria for taking into account non-proportional loading condition. So, first of all, I will move to the summary of my presentation. After a brief introduction, I will present the constitutive equation for the leverage subloading surface model and the two failure criterion we adopted for the evaluation of the metal ductility, the modified Lemaitre criterion and the modified Moore-Coulomb criterion. And then I will show some numerical analysis. So, the evaluation and the prediction of the failure behavior in materials are a fundamental aspect in the design and in the evaluation of the carrier structure. We adopted an elastoplastic and damage constitutive model for the evaluation of the failure behavior of Q460 steel, according to some experimental results we found in literature proposed by Lee in 2016. And we adopted two different failure criteria. One is the modified Moore-Coulomb, according to the presentation in 2010 of Bai and Wertzicki. And the second one is the well-known Lemaitre criteria. We chose two different shapes for the samples. One are flat groove plates, and the other one are round bar with notches, in order to highlight the role of the load angle parameter and the different notch ready in order to take into account the effect of the stress reaxiality. Briefly, without entering detail of the constitutive equation, I will just say that the model has been developed in the framework of the continuum damage mechanics and assuming the damage as a tropiscalar variable and assuming the old hypotheses that have been proposed by Lemaitre. And just for sake of completeness, I will say that the damage has been coupled through the definition of the stress rate and to the consistency condition for the taking into account the effect on the plasticity. Through some mathematical passages, we can obtain the plastic multiplier, which gives the influence of the plasticity and mutual the damage on the plasticity during the analysis. Without explaining the other constitutive equation, I would just say that the choice of this model has been done because the subloading surface model, the original one, was created in order to take into account the correct cumulative plastic strain during a cyclic loading test for low cycle fatigue or a high cycle fatigue. The characteristic of this model is to abolish the distinction between an elastic and a plastic domain, and it allows the generation of plastic strain even in the subyield state, which is the state inside the so-called conventional plastic potential, which here is named normal yield surface. In order to do that, there is a second surface, the subloading surface, which is a kind of a loading surface which expands and contracts in the stress space depending on the loading or unloading on the model. Now, focusing on the damage criteria, the first approach that we adopted a few years ago was taking into account the classic Lemaitre model, which, however, cannot take into account the effect of the load angle. So just the stress reaxiality could be caught in that damage evolution. So we suggested a kind of modification in order to take into account the effect of the load angle parameter. So we define, due to the isotropy of the material, we define a variable chi, which is a function of the principal digestoric stress, and we formulate a very simple function which modifies the shape of the failure strain in order to take into account the different loading conditions from compression to tension passing through strain, plane strain or shear. Now, the function is a simple parable, as you can see, and then it's function of this variable chi, which takes into account the different loading condition and a material parameter beta. So the ductile damage evolution law has been simply modified. This is the original part, which is function of two parameters, S1, S2, and we added another function, nu theta, which takes into account the load angle parameter. Unfortunately, according to some experiments done by Clausing in the 1980s, there is an effect of the straining hardening on the load angle effect. So basically, the load angle effect tends to decrease when the strain hardening is big. So in this case, we added another modification in order to take into account of the mitigation of the effect of the strain hardening on the load angle effect. Basically, this function tends to decrease the effect of the load angle in the ongoing of the analysis due to the strain hardening of the material. The second criteria I will present is a Moore-Coulomb failure criterion, which was previously used mainly for granular material like soil or concrete or rocks. And this is a form presented by University in 2010. This is function of the main two parameters, which are the stress reaxiality and the load angle, which is expressed differently from the previous variable chi, but basically the meaning is exactly the same, and by 8 material parameters. Now, if we take into account to neglect the effect of the pressure on the plasticity and the load angle on the plasticity, we can simplify the function of the failure criteria using the von Mises plastic potential, reducing the previous expression from 8 to 4 parameters. So this expression is much easy to use, and in first approximation it gives very good results for certain type of material. So the damage evolution law, it's, in this case, is presented simply by the function of the plastic multiplier, the damage, and the failure, the strain failure. Now, we implemented everything via use of subroutine for the commercial code Abacus, alternatively used two different failure criterion. We chose some material parameter, in this case is aluminum 2024, and we set damage parameter for both Moore-Coulomb and Lemaitre, which in order to give almost the same damage evolution. So this simple numerical example has been conducted just in uniaxial extension for a cubic element, just to show the robustness of the model that can integrate the constitutive equation both in explicit and implicit return mapping strategy. And it shows that the model can, even in implicit integration, catch very well the damage evolution and the stress strain evolution. Now, switching to the main calibration, we chose to refer to the data presented by Lee and other in 2016 for a construction steel. As I said, we used two different set of samples, round notch bar and flat groove plates. We took exactly the same material parameter that were given by the experimental analysis given in the reference paper, and then we calibrated the set of the material parameter. If you recall the previous slide, the Lemaitre model needed just two material parameters, S1, S2, in the uniaxial analysis because there is no load angle effect, so basically it's very easy to calibrate. The Moore-Coulomb one required always more parameter because we have to define the strain envelope, the failure strain envelope. So in this case, I will show how we obtain this material parameter. So first of all, we set a heavy step side function, which is a function of one material parameter d1. Basically, this is needed because some material don't show some damage for a certain amount of plastic strain. So this parameter d1 can be easily obtained by performing some loading, unloading, and reloading analysis, and showing the variation of the Young modulus. The Lemaitre model can calibrate the first two through a smooth round bar, and calibration for the load angle function has been done taking into account the maximum equivalent strain among the samples, and by calibrating one flat groove plates for taking into account of the effect of the load angle. The Moore-Coulomb can be done through a minimization process, taking the experimental results and then fitting the surface that pass closely to all the experimental evidence, or can be alternatively done by minimizing the difference between the load displacement curve for at least 3 samples for taking into account the calibration of all the parameters. Now, the numerical results for all the different samples shows that basically both of the criteria give a good description in terms of load displacement curves and the prediction of the final displacement to failure. Actually, the Moore-Coulomb criteria gave a better description in terms of the final displacement to failure, but This is just a matter of calibration. If we have infinite time to calibrate the material, we can obtain very good results for both the approaches. But I have to say that the calibration of the Moore Coulomb is much easier than the Lemaitre model, because we always have the size and the shape of the failure envelope, so it's easy to set the material parameter. For what it concerns the failure to pass, we can plot the equivalent strain to fracture against the load angle and against the stress reaxiality. Now, everybody knows that the stress reaxiality and the load angle are not a constant during the analysis due to the effect of the notches, which makes a variation during the tensile test. So we assume the average approach proposed by Bao and Bergsvik in 2004. And if you look at the average values, they actually can catch quite well the numerical prediction made by Lee in 2016 and intersecting the correct failure envelope that we set before. And if you want to have an outlook of where the material failed, we have the uniaxial extension, which fails according to the size of the radius notch and the plate strain. Just since I'm running out of time, these are just on contour field of the damage. Basically, the model can predict the correct location of the crack formation, the maximum damage element, which are always in the center of the plate. And the contour field between the Lemaitre and the Moore Coulomb one are basically almost identical. Same thing can be said for the damage contour field of the uniaxial extension. The prediction is of the damage at the center of the bar. For the smaller notches radius, there is an effect of combination between plastic strain and stress reaxiality. At the beginning, the damage starts on the surface due to the effect of the plastic strain, but then it shifts in the core of the bar due to the effect of the stress reaxiality. As a conclusion, this is the first presentation that shows the performances of the model for calibration of a standard steel for construction steel. Both of the criteria can be used in the calibration of the ductile behavior of steel or metals in general. And in the next presentation, I will show additional modification to take into account the different mechanism of the definite evolution through proportional and non-proportional loading condition. Thank you very much for your attention. These are some references.